Okay, so in review from last time, we briefly talked about hydrogen bonding being a special kind of bonding. And so what I want to show you is hydrogen bonding happens, again, only between between hydrogen and 1 to 3 molecules. And those three, atoms or elements. And those three elements are oxygen, nitrogen, or fluorine. Change this color here. Okay, so again, oxygen, I can't write over. Oxygen, nitrogen, and fluorine. So if I look here, this is an oxygen being the donor atom to the hydrogen of another water. Here's nitrogen being the donor and ammonia being the donor to another ammonia with a hydrogen. Here's oxygen being the donor to hydrogen of the ammonia. Here is nitrogen being the donor to hydrogen. And this is HF, fluorine being the donor to the hydrogen of ammonia, or nitrogen being the donor to HF. The one they don't have shown here is I can have an HF-HF bond also, with fluorine being the donor and hydrogen being the exciter. Okay. So now, how do we go about identifying the intermolecular forces? Okay, so first thing we have to ask is, does the molecule have a nitrogen, oxygen, or fluorine, and have a hydrogen? And this hydrogen must be bonded to the nitrogen, oxygen, or fluorine. Okay, so I can have lots of hydrocarbon molecules that have carbon, hydrogen, and oxygen in them that won't count as a hydrogen bond because the hydrogen is not bounded to the oxygen but to the carbon. Okay, so that's why I say that. Is the molecule polar or nonpolar? And of course, every molecule has London dispersion. So all molecules have London dispersion. Polar molecules have London dispersion and dipole-dipole. And molecules that have nitrogen, fluorine, oxygen with bonded with hydrogen have London dispersion, dipole-dipole, and hydrogen. So the strength of the forces goes that London dispersion is the weakest, dipole-dipole is the middle, and hydrogen bonding is the highest, not only because it's got the strongest interaction, but because a molecule that has hydrogen bonding also has dipole-dipole and London dispersion. So what would be all the, and this IMF stands for intermolecular forces, that would occur for each of the following? Okay, so I have CCl4. So a lot of times, again, you're going to have to draw out the little structure for these to tell if something is polar or nonpolar. So real quickly, carbon has 4 valence electrons. I'm going to start shortcutting this. Chlorine has 7 times 4, which is 28. So that gives me 32. So it's carbon with 4 chlorines around it. That used up 8, and then 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And that's carbon tetrachloride. Okay, so this is a tetrahedral molecule, so this is a non-polar molecule. Okay, and as such, it only has London dispersion. So the only force that carbon tetrachloride has is London dispersion. Okay. Oops. I don't know what that just did, but it didn't want to do that. There we go. This is what I want. All right, for sulfur dioxide, sulfur has 6. Oxygen has 6 and there's 2, so it's 12. Gives me 18. Sulfur is my center atom, so there's 2 and 4, 6, 8, 10, 12, 14, 16, 18. Okay. Just because of proper drawing, this only sees 6, so it's going to form a double bond. It doesn't matter which oxygen. It has a resonance description, but that doesn't matter. So that's the structure. It has no hydrogens, so therefore it doesn't have hydrogen bonding, but this is a polar molecule. And so as such, the intermolecular forces are dipole-dipole, and then all of them have London dispersion. Okay, so that's how you do that one. Okay, you should pause the video and try to do bromine fluoride here. But basically each one of those has 7, so it's 14. There's only 2 atoms. It doesn't matter. There's not really a center. That's 2, 4, 6, 8, 10, 12, 14. Because these are 2 different atoms, it automatically makes this polar. And as such, it has a dipole-dipole. And London dispersion. Okay, so that's that one. Again, you should pause the video and try to do the phosphorus pentafluoride on your own. But phosphorus has 5, chlorine has 35, so I have a total of 40. Phosphorus is my center atom with 5 chlorines. And I'm going to switch colors for these long pairs just so it's something different. Okay, so that was 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, so this is a trigonal bipyramid, and it's nonpolar. And because it has no zero lone pairs, so therefore the only one that this one has is London dispersion. Okay. Also, rank the following from weakest intermolecular forces to strongest. Okay. If it's a diatomic atom like iodine or nitrogen, it's gonna automatically be nonpolar. So both of these are nonpolar, so both of these have London dispersion. I'm just going to put an abbreviation underneath it. Okay. This has hydrogen, but that's not there. If I were to draw the structure, it looks a lot like water, except for the fact it's sulfur instead. So it has the dipole-dipole and London dispersion. And of course, this is hydrogen and oxygen, so this one has hydrogen bonding, London dispersion, I think one order, and dipole-dipole. Okay, so therefore, this one's going to be the strongest. These two both have London dispersion only, so when I have 2 that have the same force, I have to look at the molar masses. This has a molar mass of 28. This has a molar mass of, I think it's 253. Oops, 3. Somewhere around in that area. So therefore, nitrogen is my weakest, followed by iodine, then H2S with the dipole-dipole, followed by water having the strongest because it has hydrogen bonding to it. Okay. All right. Next slide is list the following in order of increasing boiling points. So the thing about this is that the higher the intermolecular forces, the higher the boiling point. Okay? So basically first have to find out what the intermolecular forces are. Okay? Carbon monoxide is going to be, because it's 2 different atoms and only 2 different atoms, it's going to be a dipole-dipole and London dispersion. HF is one of those that has hydrogen bonding. I need to change colors here because I'm too close there. All right, so this one has hydrogen bonding, which also means dipole-dipole and London dispersion. This one is an atom by itself, so it has London dispersion only. Carbon dioxide is a linear molecule when you draw it out, so it also only has London dispersion. So again, I need to look at the molar masses of these two. Okay, neon is 10, I believe. I need to have a periodic table on this one. Carbon dioxide is 12 plus 16 plus 32 is 44. Okay, so neon has the lowest intermolecular forces, so it's going to have the lowest boiling point. So neon is first, okay, followed by the carbon dioxide, followed by carbon monoxide, followed by HF. Okay, and we know for a fact that these three all are a gas at room temperature, so they have a fairly high, fairly low boiling point. Okay. And for the last question is, which is likely to have the higher vapor pressure? So one thing to think about is the higher the boiling point, the lower the vapor pressure. Which means that the higher the intermolecular forces, the lower the vapor pressure. Okay, so this is asking you to compare two things. Okay, this one is linear. I'll draw it. I didn't draw it out on the last slide, so I'll draw it out on this one. So that's what carbon dioxide looks like. Sulfur dioxide I drew a couple slides ago. It is a bent molecule. So this one's polar. So this one has dipole-dipole and London dispersion. This one has, so this is dipole-dipole and London dispersion. This is London only. So therefore, it wants to know which one has the higher vapor pressure. So the higher vapor pressure is going to be the CO2. Okay. Now this one, the way this is drawn out is basically you have a carbon and a hydrogen are bond together, and then comes the next atom. So it's carbon, oxygen, hydrogen, and these three hydrogens here come off. It's called a condensed structural formula. Versus this one is carbon, oxygen, carbon, and I have three hydrogens off each one of the off each one of the carbons here. Okay, you'll do a lot of this next year in organic chemistry. All right, so when I first said about hydrogen bonding, remember a couple slides ago, I said the fact that the oxygen and the hydrogen have to be bonded together for hydrogen bonding to occur. So in this molecule, I have no hydrogens bonded to the oxygen. And this one, I have the oxygen and the hydrogen bonded together. So this one has hydrogen bonding, which of course is dipole-dipole, and London dispersion. Because I have two lone pairs on this oxygen, it's going to be bent around that, so it's going to be dipole-dipole, it's still polar, and London dispersion, but it doesn't have the hydrogen bonding. So therefore, this molecule here is going to have the higher vapor pressure. Okay, and I think that's the end of this lesson.